Now that we've introduced the mean value theorem, let's go over a couple of examples of making use of the mean value theorem. So first and foremost, for the following functions, verify they satisfy the two hypotheses of the mean value theorem, then find all values of c guaranteed by the conclusion of the mean value theorem. So for the first function we have f of x is equal to the square root of x plus 3. The given interval is the closed interval from -3 to +6. So the first thing that we should point out is that f is a root function which is continuous on its domain. Now, because it is a square root function, we do need that x plus 3 is greater than or equal to 0, telling us that the domain is going to be that x is greater than or equal to -3. In interval notation, that would be the half closed, half open interval from -3 to +infinity. Now, this closed interval is contained within this interval, so we are okay. Therefore, f is continuous on the given closed interval, -3 to +6. Now, this is where the differentiability thing is going to come in really handy, or rather be really significant. So first thing we'll do is actually take a derivative. So we are about to take the derivative of, we'll call that x plus 3 raised to the 1/2 power. Applying the power and chain rules, that'll be 1/2 times x plus 3 raised to the -1/2 power, or and then multiplied by an extra factor of 1 from the chain rule. Put more simply, this would become 1 over 2 square roots of x plus 3. Now with that in mind, by taking a derivative, we have altered the domain of this critter, because we can no longer include -3 as part of the domain. This is why it's super important that for the continuous factor, it's the closed interval, but for the differentiable factor, it is the open interval. Therefore, f is differentiable on the open interval from -3 to 6, which is what we need for the mean value theorem. Now that we've gotten both of those, we'll also need the slope of a secant line joining those 2 points. So that'll be f of 6 minus f of -3 all over 6 minus -3. Plugging 6 into the original function, we get the square root of 9. Square root of 9 is 3. Plugging -3 back into the original function, we get 0. Additionally, 6 minus -3 in the denominator is 9. Therefore, the slope of the secant line is going to be 1/3. So we are going to set f prime of c equal to 1/3 and see if we can find a c on the open interval from -3 to +6. So we already got the first derivative from testing differentiability, so we will be setting 1 over 2 square roots of x plus 3 equal to 1/3. Now some would call it cross multiplying, some would call it take the reciprocal of both sides, but we need that 2 times the square root of x plus 3 is equal to 3. Divide both sides by 2, we get square root of x plus 3 is equal to 3/2. Squaring both sides, we get x plus 3 is equal to 9/4. And finally, subtracting 3 from both sides and getting a common denominator, we will get x is equal to -3/4. This should really be c all the way throughout here. Well, we'll just change it at the end because why not? So c is equal to -3/4. That'll work. I'll try to do better on the next one. Speaking of the next one, let's try this out again. This time I'd like to use the function f of x is equal to e to the x, and I'd like to use the closed interval from 0 to 2. So the kind of function that we're dealing with, f is an exponential function, which is continuous on its domain. Domain of this exponential function is going to be all real numbers. Therefore, f is definitely continuous on the closed interval from 0 to 2. So no problem there. When we take a derivative of this function, I'm about to take the derivative of e to the x, I'm just going to get e to the x once again. It's one of my favorite things about the function e to the x is that it is its own derivative. The domain of this exponential function is the same as the domain before because it's the same function. Now the open interval from 0 to 2 is definitely contained within all real numbers, therefore we can say f is differentiable on the open interval from 0 to 2. So that takes care of the two hypotheses of the mean value theorem. We'll also need the slope of the secant line, which in this case will be f of 2 minus f of 0 all over 2 minus 0. F of 2, we plug in x equals 2 to the original function, we get e squared. Minus, we plug in x equals 0 to the original function, we get e raised to the 0 power. Anything raised to the 0 power is simply 1. Denominator is 2 minus 0, which is simply 2. There's no way to simplify this in any sort of effective fashion, so what we're going to do is set f prime of c equal to this slope, and then we are going to solve for c. That is e raised to the c power. Hey, I remembered to do c this time. Good for me. That's e to the c is equal to e squared minus 1 all over 2. We can solve for c by taking the natural log of both sides. We get c is equal to the natural log of e squared minus 1 all over 2. Now, it may not look all that pretty, but I guarantee you that is the correct exact version of the final answer. If you're interested in verifying that this thing is actually on the appropriate interval between 0 and 2, you are welcome to approximate this answer. Now, in approximating this answer, we are going to see natural log of extra set of parentheses for the numerator, e squared minus 1, and then divide that by 2. We want to make sure that this number is between 0 and 2, and the calculator helps us verify that it is in fact between 0 and 2. So that's about 1.16, rounding at the second decimal place. Let's do one more example so that we can see a situation where you could potentially have more than one value of c within your given interval. Here's an old friend of ours that showed up for Rolle's theorem. Oh no, sorry, I changed this number a little bit. So no, we haven't seen this before, but we're going to make it work. So first thing to point out is that f is a polynomial function which is continuous on its domain. Boy, that's a phrase we've used a lot. And the domain of any polynomial function is all real numbers. So given that the domain is all real numbers, we can have basically any closed interval in here, and that'll work out just fine. So f is continuous on the closed interval from 0 to 4. And if we take a derivative, and for that derivative, I believe we will make use of the product, power, and chain rules. Of course, we could expand this. You know what? I changed my mind. I'm going to expand this thing completely, then we'll take a derivative, because I think we're going to need to do some algebra with this anyway. So expanding the square first, we'll get x squared minus 6x plus 9, and then distributing the x through, we'll get x cubed minus 6x squared plus 9x. Completing each of those derivatives according to the power rule, that'll be 3x squared minus 12x plus 9. Now this is still a polynomial function. That polynomial function still has a domain of all real numbers. Therefore, we can conclude that f is differentiable on the open interval from 0 to 4. Finally, we're going to need a slope of the secant line. Slope of the secant line is going to be f of 4 minus f of 0, since those were the x values that were given to us, all over 4 minus 0. So plugging in x equals 4, we're going to get 4 times 4 minus 3 quantity squared. That's 4 times 1 squared, that'll be 4. And plugging in x equals 0 will give us 0 times, I don't really care because it's 0 times something. So that's 4 minus 0 over 4 minus 0. That's going to simplify to 1. Therefore, we are going to be setting f prime of c equal to 1 and solving for c. So that'll give us 3c squared minus 12c plus 9 is equal to 1. This quadratic equation can be solved in a couple different ways. I think I am going to go with, let's go with the quadratic formula. Now in order to use the quadratic formula, first thing I'm going to need is a 0 on one side. So we'll subtract 1 from both sides. And then say c is equal to opposite b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now this does simplify pretty nicely. This will be positive 12 plus or minus the square root of, that's 144 minus 96, that'll be 48 all over 6. Simplifying this radical, we can break a 48 into a 16 times 3. So square root of 16 gives us a 4. So 12 plus or minus 4 square roots of 3 all over 3. Or if you want to distribute, all over 6. Then if you want to distribute the 6 to both of the terms, we'll get 2 plus or minus 2 square roots of 3 all over 3. So that's distribute the 6 and then reduce each of the fractions. Now we are looking for all values of c that are between 0 and 4, and we can use our calculator to verify that both of these answers are within that interval. So that'll be 2 plus 2 square roots of 3 divided by 3. That is on the interval from 0 to 4. Then if you press second followed by enter, we just need to change that plus sign to a minus sign and verify that that is also on the interval from 0 to 4. Now if you take the time to graph this thing and look at it on the appropriate interval, I think it'll explain pretty nicely why things are the way that they are. So x times x minus 3, quantity squared. For the window, we're going to go from 0 to 4 for both x as well as y. So here's what the graph of the function looks like. It is cubic in nature. So you could think of the slope of the secant line, or think of the secant line as the line connecting these 2 points. If you move it in a parallel fashion, you can see that there will be a tangent right up there toward the top of the function, and then another tangent right down this, right down this way toward the bottom of the function. So that was 2 minus that fun radical, and then 2 plus that fun radical. So hopefully this gives you a decent grasp of what's going on with these mean value theorem problems.